Welcome to The Explainer. Today, we're staging a high-stakes bake-off between three different AI models. Their mission? To solve a really tricky environmental puzzle that has, for years, been a tough nut for scientists to crack.
Let's just start with a question that sounds super simple, but it has some pretty profound implications. Can we actually, accurately measure the amount of life in a patch of ground, what scientists call biomass, just by looking at a photo?
So why does this even matter? First, let's break down why measuring biomass is so incredibly important, and honestly, why it's been such a headache to do traditionally.
Okay, so biomass is just the sciencey term for the total weight of all the living stuff in one spot. We're talking green leaves, dead leaves, the whole shebang. It's a really key indicator of how healthy an ecosystem is. The problem is, measuring it the old-fashioned way means you have to physically go out there, collect samples, lug them to a lab, dry them out, and then weigh them. It's a lot. It's slow, it's expensive, and it's almost impossible to do on a large scale.
But what if there was a better way? This is exactly where AI swoops in. It has the potential to completely change the game here, letting us monitor the health of our planet on a massive scale, just by analyzing pictures.
So how in the world do we teach an AI to see biomass in a photo? Well, the answer lies in this really clever two-step process. Think of it like a two-part system. First up, we use this super powerful image recognition model called DINOv2 to act as the eyes. It scans the photo and pulls out all the key visual features, things like textures, shapes, and colors. Then all that info gets handed off to a second model, CatBoost, which acts as the brain. It takes those features and crunches the numbers to predict the final biomass amount.
But how do we know which AI is really the best for the job? We need a fair fight, a rigorous competition, with a crystal clear set of rules to make sure it's a level playing field.
To judge our AI contenders, we're going to use a metric called the weighted R-squared score. Just think of it like a final grade on an exam. And the weighted part here is absolutely crucial. It means that getting the total biomass correct is worth more points. It's all about nailing that big picture number.
So here are the rules for our bake-off. We've got three contenders, small, base, and large versions of that DINOv2 vision model. To keep things fair, each model gets tested 5 separate times on different chunks of the data. The winner is the one with the highest average score. But we're also keeping an eye on efficiency. Is it a nimble little speedster or a big, gas-guzzling giant? Size really matters here.
All right, the stage is set. Let's meet our three contenders and see how they actually perform when the pressure's on.
First up, we've got ViT-Small, our lightweight contender. It's the smallest and most agile of the bunch, really built for speed and efficiency. And looking at its scores across the 5 tests, pretty solid. It peaks at a very respectable 0.65, but it also has a couple of dips down to 0.46 and 0.48. So it's a strong contender for sure, but there's a little bit of variation in its results.
Our next contender is the middleweight ViT-Base. This one is designed to be the best of both worlds. A good balance of power and efficiency.
And wow, its performance is remarkably consistent. Just look at these scores. It's consistently hitting the mark. 4 out of the 5 scores land in that sweet spot between 0.54 and 0.63. That shows a really high degree of reliability. It's a steady hand.
And finally, the heavyweight champion, ViT-Large. This is the biggest, most powerful model in our lineup, a real titan of AI.
Now, the results for ViT-Large are fascinating. On one hand, it achieved the single highest score of the entire competition, a stellar 0.67. But on the other hand, it also turned in the absolute worst performance, a pretty disappointing 0.36. This tells us we've got a model with huge potential, but a troubling lack of consistency. It's a bit of a wild card.
So, the competition is over, the results are in. Let's break down the final scores and see what we can actually take away from all this. When we average out the scores, the base model, ViT, comes out on top with a score of 0.569. But that's only half the story. Look at the sizes. The large model is a whopping 1.1 gigabytes, while the small model is a lean, mean 84 megabytes. That is a massive difference in how much resource they need.
This chart gives us a fantastic visual of the results. You can see ViT-Base right there with the highest average score. But notice that error bar on ViT-Large. That long line, that represents its wild inconsistency, a visual confirmation of what we saw in its scores.
So here's the bottom line, the crucial point. It's all about the trade-off. If you want pure, consistent accuracy, ViT-Base is your winner, hands down.
But if you're talking about efficiency, the best bang for your buck, ViT-Small is the undisputed champion. It gives you performance that's almost as good as the big guys, but at a tiny fraction of the size.
And this just highlights a core lesson in the world of applied AI. While raw power is always impressive, for real-world use, you have to balance performance against practical things. Efficiency, size, and reliability often win the day over just brute force.
And this whole thing leaves us with a really tantalizing question. We've just seen how AI can measure the life in a landscape from a single picture. So what's next? What other hidden, complex things about our world are just waiting to be revealed, all through the lens of a camera?